Okay, so today we are going to finish our considerations about the hyperboloid. To begin with, I would like you to show that every rotation around the vertical axis, around the z-axis, belongs to the restricted Lorentz group. So that every rotation around the z-axis is an orientation preserving Riemannian isometry of the hyperboloid. This exercise, which is not hard at all, I'm going to use to prove that for any 2 points in the hyperboloid, there always exists a shortest curve that connects them. So remember that the action of the restricted Lorentz group on the hyperboloid is transitive, so that we can always take a matrix that moves one of our points to n. Okay, so once we have put one of our points in n, once we moved it to the point 0, 0, 1, the next thing I'm going to do is to rotate so that the other point then sits on the xz plane. So I take a rotation such that BAQ lies on the xz plane. Okay, so of course notice that B fixes n, right? Being a rotation around the z-axis, it fixes n. Okay, now at this point we see that then that BAQ is of the form hyperbolic sine 0 hyperbolic cosine of a real number T0, right? That's because the cross section of M in the xz plane is a hyperbola, right? As we saw earlier in the course. Okay, now we already saw that this curve, the curve that starts at n with the initial velocity vector 1, 0, 0, is a shortest curve connecting n to this point, right? And actually we saw that it's parameterized by arc length. Okay, right, but then once we have our shortest curve from n to BAQ, then we can simply undo the isometries we took, right? So we obtain this curve, which is then a shortest curve connecting P and Q, right? Because A inverse and B inverse being Riemannian isometries, they preserve the property of something being a shortest curve, right? As we saw also earlier in the course. So the result follows. Now notice that something interesting is that it is possible to compute explicitly A and B in terms of P and Q. In other words, actually, I would say that it is possible to write a program giving a program that has P and Q as inputs, and as output gives the shortest curve connecting them. Okay, now as we saw earlier, once we have a shortest curve, of course the length of that shortest curve is equal to the distance between the points, right? Because the distance was defined as the infimum of all the lengths of all the curves connecting them, right? Of all the hyperbolic lengths. Okay, now of course also since the orthogonal Lorentz group, since its elements are actually Riemannian isometries of the hyperboloid, then they have to preserve this distance, right? So we have this equality for all elements of the orthogonal Lorentz group. So remember that the orthogonal Lorentz group is defined to be the set of all matrices in O2-1 that preserve M. So that it's all those matrices that preserve the Minkowski form and do not exchange the two sheets of the hyperbola, right? So that it preserves. They preserve M. Okay. In other words, the Riemannian isometries are also metric isometries. Right? Okay. So here's some exercise, which says first that if you give me these 2 points, if we require that CP is n, so that we move one of the points to n, and the other point we move it not only to the xz plane but actually to the xz plane with a positive x entry. Determine that this then C is determined uniquely. Then compute C explicitly. And then exhibit a formula for this curve, right? So it's what I mentioned a few minutes ago. Just only that this condition determines C uniquely. Okay. Now we are going to give a formula for the distance between 2 points. Well, for the hyperbolic cosine of that distance, and I would say it's a beautiful formula, it's a beautiful relation, because the theorem is that the hyperbolic cosine of the distance between 2 points is given completely in terms of the Minkowski pairing of the points. So let's prove it. So the equality is obvious if P is equal to Q, right? Because in that case, if P is equal to Q, here this becomes 1, right? Because P being in the hyperboloid means that P is minus 1, so this becomes 1. And the distance between P and P is 0, and the hyperbolic cosine of 0 is 1, right? Because e to the 0 plus e to the minus 0 divided by 2 is 1, right? Okay, so let's suppose that P and Q are actually different, and let's move them to n and the xz plane. Okay, I mean, kind of remembering that we have the freedom to apply the elements of the restricted Lorentz group without affecting neither the distance or the Minkowski product, right? So we have a lot of freedom. Okay, so we saw, I mean, the distance between n and this point is actually T naught, right? It's precisely this. This we already saw. Okay, so T naught is then also the distance between P and Q, right? Okay. Now, on the other hand, the hyperbolic cosine of T naught, well, we can obtain it by pairing this with the n, right? Because pairing it with the n is the point 0, 0, 1. It gives us, the pairing gives us just minus this product, right? So this cosine is minus the pairing. But this pairing, you know, since n is equal to AP, then of course the pairing is equal to just the pairing between P and Q, and we are done. So this is, I would say, a really nice formula. Now let us define the exponential function at each point of the hyperboloid, and it is given as a function from the tangent plane to m, and the value at any tangent vector is, you know, we take the curve gamma that starts at P with this with V as initial velocity vector, and then we take its value at 1, right, at time 1, and that's the exponential. Okay, and yeah, so this is the curve we defined earlier, right? Namely, it's given by this rule. Okay, and now we can prove that this exponential map is surjective. So let us use the notation from the theorem, from the first theorem we proved about existence of shortest curves. So you see, so we have this curve, which is parametrized by arc length, right? It's parametrized by arc length because the norm of this one is 1 of this tangent vector is 1. Okay, so we parameterize it by I mean, we want to parameterize it not by 0 T naught but by 0, 1. So we do that, and it can be, it's easily seen that this can be achieved by simply taking, instead of this initial vector, taking T naught times that vector, namely T naught 0, 0 as initial velocity vector. Okay, so it's somehow this one has the same trace as the other one, but it's traversed at a different rapidity. That's the point. Okay, and we see that then since this one connects P to Q, we see, and since you see now at 1 it gives us Q, we see that the exponential of this tangent vector is Q. So what we have proved is that you know, if we fix P and look at the exponential at that point, any point Q is of the form exponential of a vector, right? And actually, it is actually computed quite explicitly, I would say. Okay, so yeah, I think here it should be E1 maybe. Okay. Okay, so the exponential is surjective, and well, the next corollary is that you see the distance. If we take any vector, so the distance between the kind of the initial point and the point at 1. You know, after we let kind of things flow for 1 second, let's say, for 1 unit of time, this distance is precisely the norm of p, the norm of the tangent vector. Okay, and the proof is quite easy. I mean, the distance between this point and this point is precisely the length of the shortest curve joining the points, right? Which is this one. Okay, but that length we computed it, right? That this since here is the interval 0, 1, that length is simply the norm of the vector, right? So this we saw when we introduced these curves gamma PV, right? Through this rule. Okay. Okay, and finally, let us show that the image of any shortest curve connecting distinct points is contained in the intersection of M with a two-dimensional vector subspace of R3. So here what I'm going to do is I'm going to show that if you give me one of these curves, its image is necessarily contained in a two-dimensional vector subspace. And of course, since I'm asserting that the image of any shortest curve, I am in particular saying that any shortest curve in the hyperboloid is of this form. So this I will leave you as an exercise. I think if you trace the proof that these are shortest curves, if you trace those integrals, if you trace that other curve eta, I think you can prove that if eta is not a parametrization of one of these, then somehow it has to leave the image at some point, the image of this one at some point, and I think that way you can show that the length of that curve eta is strictly larger than the length of this one. So I leave you as an exercise to trace that proof that would show then that these are the only shortest curves. So I mean that every shortest curve in M is of the form gamma PV. Okay. Using that fact, what I do is okay, take any point and a non-zero tangent vector that determine then this curve. Okay, which any shortest curve is of this form, and complete V to an orthogonal basis of the tangent plane at P. So orthogonal, not orthonormal, right? Because I'm not assuming that V has norm 1. So only orthogonal basis, but that's good enough for me. Okay, and then well, just take the Minkowski pairing between this point in the hyperboloid and this tangent vector. Okay, so just you know just substitute in you know the rule for this one. Okay, and here, well, since V2 lies in the tangent plane at P, is Minkowski orthogonal to P, right? So somehow we are left with only this, but V and V2 are orthogonal, so this is 0. And what this shows is that the image of my curve is contained in the Minkowski orthogonal to V2, which is a two-dimensional vector subspace, right? Because the Minkowski bilinear form is non-degenerate, right? And V is not 0, and V2 is not 0. Okay, so we are done. And finally, some exercises. One is that one can compute this space, this vector space, explicitly in terms of the point P and V. So the exercise is to compute it explicitly, and by computing it, what I mean is to compute the homogeneous linear equation defining it, right? So compute the coefficients of that equation explicitly in terms of the point and the tangent vector. Then the next item is a shortest curve, you know, can be given in terms of as gamma of PV, kind of somehow like a differential equation shape, but also, you know, like if you give me 2 points, like let's say 2 different points P and Q, these 2 different points, as we have seen, determine a shortest curve. Okay, and then the exercise is to compute the two-dimensional vector subspace containing that shortest curve explicitly in terms of P and Q. That is to compute explicitly the coefficients of the linear equation defining that subspace in terms of P and Q. So that one can actually write a program that gives P and Q as input, and as the output gives the coefficients of the linear equation. Okay, and then the next exercise is the following. So we have seen that every shortest curve is contained in a Minkowski orthogonal, right? So this means that certain subspaces, the subspaces of this form for V2 in the tangent plane at some point intersect the hyperboloid, right? But of course, not all vectors, not all two-dimensional vector subspaces of R3 intersect the hyperboloid, right? For instance, the horizontal, you know, the XY plane does not intersect the hyperboloid, and one can find others, right? So the exercise is to completely characterize all the vectors in R3 with the property that their Minkowski orthogonal intersects the hyperboloid. Okay, and finally, I want you to think about a converse to the theorem, right? So a converse to the theorem we just proved. Namely, is it true that if we have a vector W with the property that its Minkowski orthogonal intersects M, is it true that that intersection is a shortest curve, or let's say the image of a shortest curve? So I would like you to think about that. And that's it for the moment about the hyperboloid. So as you can see, there's a lot of things that can be done completely explicitly for the hyperboloid. And so the next class is going to be about the upper half plane. That's the next model we are going to study. And afterwards we're going to go on to the disk. Okay.